Okay, relationship of building form to the use of energy. Of course, the geometry of buildings is not the only factor affecting energy consumption in buildings, and in many cases is only a minor factor. And also, as the insulation of the fabric of buildings is improved, insulation of roofs and walls and glazing, so any relationship between geometry and the use of energy for heating would become weaker. But given the inefficient and leaky state of the stock as it exists, there certainly are strong relationships between geometry of buildings and their uses of energy, which can be demonstrated empirically. And indeed, if there weren't, why should so many people spend so much time putting geometrical data into energy simulation models? I'm going to make use of three simple measures to describe the forms of buildings at an abstract or generic level so that one can generalize. And the first of my measures is the ratio of a building's surface area to its volume. Surface area S, volume V. If you look up at the building, notional building at the top left, it's a cube-shaped building, 5 meters cube, and its volume is 125 cubic meters. It has an exposed surface, counting the four walls and the roof, of 125. So if we take the ratio of surface to volume, S over V, the ratio is 1. On the right, another cubic building, but 10 meters now, 10 meters cube. Volume is 1,000, the exposed surface area is 500, 5 times 100. And so S over V is 0.5, so that a change in size with no change in shape generally lowers this ratio of surface to volume. There's less surface per unit volume in the larger buildings, and we'll see something of that effect. This is related to the reason why cube-shaped icebergs melt slower than the equivalent volume of ice cubes. My second measure is to do with plan depth, and in a simple rectangular building it's easy to measure the depth. It's obviously the short of the two plan dimensions, but even in a simple L-shaped building, here we have one wing that is 5 meters deep and another wing that is 10 meters deep. But what is the depth at the area where the two wings join, the blue area? It's undefined. And of course that problem gets more difficult with yet more complicated plan shapes. There are several ways in which one can make approximate measures of plan depth in a different kind of way. And I'm going to use this method. Look at the top here for the moment. A long building, 10 meters deep, 50 meters long, and it has a footprint area therefore of 500 square meters. Now, just for the moment, let's measure the length of the two long walls, which are 50 plus 50 is 100. And if we divide the footprint area of 500 by the combined lengths of the long walls, we get a figure of 5, which is exactly half the plan depth of 10. And this relationship holds for any rectangular plan and for any length. And you'll appreciate that as the plan gets longer, so that ratio would approach the real plan depth. So if we look at the lower figure, again 50 by 10, footprint of 500, and we now count the short walls, we get a ratio of, at the bottom, of footprint area to perimeter of 4.7. The virtue of this, of course, is that one can apply the measure to buildings of any shape and get a kind of approximate idea of their kind of depth, which can vary, of course, in different parts of the building, but one gets a kind of averaged figure. And given that many buildings, for real good reasons, tend to be limited in depth, particularly buildings that are day-lit, which I'll talk a lot more about, then, of course, built forms do tend to be extended either horizontally or vertically in order to preserve this depth, and so this is an appropriate kind of way. There are other ways in which one might derive measures of plan depth, but I'm going to use that one. and plan that ratio of a footprint to perimeter can be related to the relationship between volume and wall area. In fact, they're just the same. Here's a block, there's the footprint area F and the perimeter P. If we multiply the footprint area by height, we get the volume. If we multiply the perimeter length by the height, we get wall area. And so the ratio footprint to perimeter is the same as volume to wall area. And that's, in fact, what I'm going to use in general. Now, the third measure I'm going to use is a measure of compactness, compactness of plan. How could one measure compactness? Geographers have devised several ways of measuring compactness of the area of the shapes of territories or lakes, and we can adapt their measures to apply to building plans. Take the shape on the left. It has an area of 23 units. We measure its perimeter. We draw a square of the same area, and we measure the perimeter of the square. Then we divide the perimeter of the square by the perimeter of the shape in question, and we get a value, in this case 0.87, which is a measure of compactness. You'll appreciate perhaps that by this definition, the compactness of a square would be 1, and any other rectangular kind of shape would have values less than 1. Other people have used similar measures but have compared a shape to the area of the circle, which of course is the most compact shape you could possibly have. And there have also been people have used measures of compactness in 3 dimensions, although I'm not going to do that. But you can imagine comparing a given shape to a cubical volume or a hemispherical volume. This kind of measure of compactness was used by a group of architectural researchers in the Strathclyde University in the 60s, applied to schools, and later on we're going to see some work applying these compactness measures to schools. So these 3 measures, surface to volume, volume to wall area or plan depth, and compactness, are clearly interrelated. For example, buildings that are less compact would tend to have more wall for a given volume. But they can all be useful in isolation or together for looking at relationships with energy use. We'd expect, of course, the ratio of surface area to volume, as I said before, to be related in temperate climates to the use of energy for heating. The depths of buildings can have an indirect relationship to energy use, because there is a kind of de facto limit on plan depth, above which it's not possible to, or it's not really possible to light or ventilate the interior naturally, a kind of threshold of depth beyond which you must introduce air conditioning and permanent artificial lighting. Of course, there are plenty of buildings that can be naturally lit and ventilated that are not deep. This used to be a naturally lit and ventilated building until it was converted for the Energy Institute and other people. But above those kinds of limits, oh, beg your pardon, sorry, I jumped ahead. Going back for a moment to compactness, just here's some examples of my measure. A square has a value of 1. You elongate shapes and you get lower values. These are actually the shapes of plans of some schools, so that with plans are articulated, with branching wings, you have lower values. And you can apply the same measure to a group of shapes considered as one shape. And this is a school that consists of several buildings. Okay, going back to plan depth. In the late 19th century, early 20th, the designers of office blocks, tall office buildings in Chicago and New York were very insistent that it was not possible to rent any office rooms that were more than about 25 feet or 7.5 meters in depth. And they tell terrible tales of people who went beyond that limit and who, as a result, were unable to let their buildings. Here are some examples. You see from the scale, 10 meters here, that these are buildings that go up to about 16 meters deep, plus 7 plus 7, 14, plus a couple of meters for the central corridor. And this kind of limit was generally preserved even after electric lighting was introduced from the 1890s. This is an illustration from which many of you will recognize the manual of the LT method developed in Cambridge by Nick Baker and others, a kind of manual method for calculating energy use in office-type buildings, later computerized. And what they do is divide the plans of buildings into what they call passive zones and non-passive zones, passive on the outside. The passive zones are those which can be naturally lit and ventilated. And the limit that they set as a default is 6 meters, which is twice the typical story height. And so again, you get 6 plus 6 plus 2 would give you about 14, 15 meters for a building that could be totally naturally lit and ventilated. Okay. So armed with these various measures, let's look at some specific types of building. I'm going to take examples from houses, schools, and come back to offices. A number of researchers have studied the relations between built form and geometrical variables, in particular Kern Stamers and Nick Baker and Carlo Ratti at Cambridge, and a group led by Philip Rode at LSE and others internationally. But they've worked in general with simulations, with models. And I don't want to be critical of their work, but of course we all know the weaknesses of many of the simulation models, and also there's a certain circularity in putting geometrical variables into a model and getting geometrical results out. And so I've preferred to concentrate on studies that use actual consumption figures, even though those are much fewer. And what I'm going to show to you is, in some cases, rather exploratory and provisional. The results are suggestive rather than definitive. So let's start with houses. Of course, the standard categorization of house types, of detached and semi-detached and terrace, describes the extent of the exposure of their walls. 4 walls exposed, 3 walls exposed, 2 walls exposed. There are in principle 2 other theoretical types which don't occur very often these days. They're what I've called quarter detached. I've never seen them called that, but that's what they are. Here's some examples from Keighley. 4 houses in a group, so 1, 2, 3 and 4 at the back, and they have 2 exposed walls each. And then there are back-to-backs, which had just 1 exposed wall. In fact, these are from Liverpool. If you look at the plan carefully, you can see as the blocks go around the corners, they've got quarter detached on the corners. But most of those have disappeared because of concerns about ventilation and because of their small size. Here are some statistics from the Home's Energy Efficiency Database, HEED, on which Ian Hamilton and colleagues here in the Energy Institute have done a lot of analysis. And HEED has, I forget how many million houses in it now, but this is a random sample of about 1 million houses, all of which are heated by gas. There's no electric heating here. And these are the types, and these are the numbers. About half of that million sample didn't have the type specified. And if you look in this column here, this is the kilowatt hours, use of gas, annual use. And you'll see that consumption does indeed fall nicely as the number of exposed walls becomes less. Becomes fewer, I should say. And the same happens with bungalows, going from detached bungalows to semi-detached. With flats and maisonettes, we can't say very much because those might have 1, 2, 3, or even 4 exposed walls. So that's not very surprising and is all very nice. And I might be tempted to pass on, but I expect some of you in the audience might say, hold on, there could be some other effects going on here. And in particular, one might expect that average house size would be larger for the detached houses and smaller for semi-detached and smaller still for terrace, which is indeed, of course, the case. The HEED database doesn't actually give floor areas, doesn't have any size information at all except numbers of bedrooms. So well, Jason Palmer from Cambridge very kindly sent me these figures from the English Housing Survey, which show mean floor areas for the 4 types as well as for flats. And again, as you'd expect, there's this kind of decline in the size from going from detached to semi-detached to end terrace to mid-terrace. So how can we now look at the relative effects of size and exposed surface? Well, what I've done is I've used these floor areas. This is rather theoretical, but anyway, for what it's worth. I've designed a detached house at the top, semi-detached, end terrace, mid-terrace. It's perhaps a mistake to make my headlines in red, but anyway. And I've assumed in every case they're on 2 stories, and I've had a story height of 2.5. I've made the depth 7 meters in every case, and I'll explain why in a second. But then I've used the English Housing Survey floor areas to derive the frontage, the width. So you can imagine on 2 stories I've now got the correct floor areas. The reason I've taken 7 meters for the depth is shown in these graphs. These are results from a survey that Frank Brown and I did in the 1980s, 300 dwellings in Cambridge, where we made plans and measured them. Here the x-axis shows the depth in meters, and the y-axis is the number of examples in each of these groups of terrace and semi-detached and detached and flats. And you'll see, you perhaps see that read the figures, that the mean is close to 7 or 7.5 meters in each case. And this is because of that they're all daylit, and because average room sizes are 3 or 4 meters square. 2 rooms together makes about 7. So this is a demonstration of Steadman's law that all houses are 7 meters deep. So equipped with those calculations from those theoretical models, here are the actual floor areas from the English Housing Survey. Here are the volumes of my little models. Here are the exposed surface areas. And these are the ratios of surface to volume. And the interesting thing about this is that as houses get smaller, the ratio gets smaller. So there is still more exposed surface relative to volume in the detached houses than there is in the semi-detached and in the terrace. If you remember, going back to my very first illustration of cube-shaped buildings, as you made them larger, this S over V got smaller. Surface became less. So the ratio of surface per unit volume decreased. Here it goes the other way. So there are these 2 effects working in different directions: size and exposed surface. And in this case, I propose to you that exposed surface is the more powerful of the effects. There's a third consideration which would come into the mix here, and that is, of course, that one would expect people living in larger houses to be richer and to have more bits of energy-using equipment, or be more profligate, or having higher temperatures. And indeed, if you plot, as Ian Hamilton has done, he's plotted here on these y-axes, this is electricity use and gas use annually. The blue is gas, the red is electricity, and this is income in quintiles. So this is the highest income group, this is the lowest, and indeed, as again you'd expect, energy use is going up with income. But I don't know, well, I haven't seen, I'm sure one could do it, but I haven't seen any statistics on income by housing type. and it would be interesting to look at that. At this point, my statistical skills, as such as they are, begin to be rather inadequate, but I'm sure this would benefit from a bit more work. Okay, so that's houses. Turning now to some non-domestic building types, let's think about schools. Sung Min Hong, who's there at the back, and Greg Patterson and others at the Institute have been looking at energy use in schools, in large samples of schools, using actual consumption data. The current, we'll come to their work in a moment, the current stock of schools in England is of course made up of buildings of different dates, buildings up to 100 years old and more. I've made a study of English elementary schools in my new book, Building Types and Built Forms, starting in 1870 when schooling became compulsory in Britain for the first time, and going up to about 1940. And just to give you a very quick potted history, the schools that were built at the beginning of this period, particularly by the school board in London, were called central hall schools, and they were called that because they had central halls with the classrooms grouped around, which meant that they were very deep buildings. They went up to about 16 meters. This is the Ben Jonson School in Stepney. It doesn't exist anymore, but this was the kind of model for a large number. In fact, the board built in London 500 schools. They got 500,000 children into education for the first time. But at the turn of the century, these schools started to be criticized. Because of their depth, they were difficult to ventilate. Standards of lighting were not good away from the walls, the window walls. And it was not possible, of course, to orient all the classrooms optimally. Here's a group of these schools, 1880s. But from the beginning of the 20th century, there was a tremendous emphasis on changing school designs to benefit children's health. There was a lot of worry about the health of school children, their lack of sunlight and daylight. And these so-called pavilion schools were designed by architects working with medical officers of health, and they were typically much shallower in plan. This is Highfields here. You see with these verandas between the classrooms exposed on three sides, a lot of ventilation. This is Darlaston, girls, boys and infants, again, shallow plans, 9 or 10 meters, through ventilation, and some borrowed light through the corridors into the backs of the classrooms to improve the lighting at the rear. There was a lot of emphasis on orientation and on sunlight. These are, I call them long straight schools. They're a lot built in the 20s and 30s in Britain. All the classrooms facing south. Again, shallow plans, facing southeast perhaps. They became very elongated, and perhaps because of that, there was a type known as the finger plan, which cut up those long lengths into shorter sections. Again, with classrooms facing south, very shallow. Here the circulation, this is a single-story school, is all actually in the open air under covered ways. And the kind of culmination of this trend, the so-called open-air schools, where the classrooms were in detached buildings of their own with glazed walls that could be folded back, and so here are the children sitting more or less in the open air. They did that not just in the summer, but in the winter as well. And of course, the plans there were extremely shallow and very well ventilated. So I've measured surface to what have I measured? No, this is a big one. This is volume to wall area. So this is a measure of plan depth in this sample of schools, this historical sample. And I've actually designed theoretical examples of each of the types with differing numbers of classrooms, so 6, 8, 10 and 12. And the school types are arranged more or less chronologically, so the central hall, the pavilion, the long straight schools, the finger plans, the open air schools. And look down this column of 6 classroom schools, so they're directly comparable. And you'll see that at the beginning, this measure of volume to wall area is about 6. So that's half plan depth. Actually, we've got to allow a bit more because these are squarish plans. So that's, they're 15, 16 meters deep here. Going down continuously through this period, getting to about 2 with the open air schools. And this is this measure of compactness, which I described at the beginning. So again, same format of this chart. Classroom 6, 8, 10, and 12, the same school types. And look down this column. The Central Hall schools are very close to 1 compactness. They're close to square in their plan, about as compact as you could get. And as the plans become more articulated, more spread out, and even fragmented in the open air schools, so this value drops down to 0.4. Now, can we see some of these geometrical properties reflected in energy use in today's school stock? Of course, mine is a historical collection of plans, doesn't go beyond 1940, and in fact, after the Second World War, there was a trend, to some extent in the opposite direction, back towards more compact schools in order to save on the amount of circulation, double-loaded corridors, in order to reduce expense on external walls. But we can be sure that the current stock contains examples of these kinds of types, and that there'll be others from late 20th century, early 21st, and that we can find variations in, say, compactness between these kinds of values. Sung-Min Hong and Greg Patterson have collected detailed data on a sample of about 500 English schools. And these are all schools with display energy certificates, so we know how much gas and electricity they use, and also a bit more, for example, whether they have natural ventilation or mechanical. None of the schools in this sample is electrically heated, and Sung-Min and Greg collected a great deal of more information by a combination of methods. They found online sources, they looked at Google Maps, they used Bing Maps, and measured a series of, I'll show you a list in a moment, but here are some examples of the ways in which they measured geometrical properties. So top left, A, measurements from digital maps of footprint area and perimeter length, measuring plan depth. These two are measures of the obstruction of the facades of buildings with other buildings or with vegetation in this case. And this criteria set here is that these are obstructions that are at or closer to a distance equal to the height of the building. And here is measurement of window areas in order to calculate glazing proportions, glazing ratios. And they made a lot more other measurements. And Sung-Min has developed a long list of characteristics going from the literature that might be expected to affect energy use in schools, not just these geometrical ones, but others, and has looked at the correlations of those measures with electricity use and gas use, or fossil fuel use for heating in primary schools and secondary schools, and has retained those variables that had a measurable impact. So that here, this is primary schools, these are secondary schools, this is electricity, this is heat. And these are the ones that are important in each case or have an effect. The top half are continuous variables, so there's floor area. Now this is, we're looking at energy intensity per square meter, so in effect floor area will be a size measure. Okay, it might be that energy intensity could be different in schools of different sizes. Building age could have all kinds of effects, leaky fabric and so on. Surface to volume, in fact, Sung-Min should be volume to surface. He actually reverses the ratio, but it's okay, it doesn't matter. Got to change that in his thesis. Building depth, compactness, glazing ratio, and pupil density. And then here are binary variables, yes or no. So glazing type single or double, whether the facades are obstructed or not, or north or south, whether there is external shading on these three facade directions, and roof lights, and whether the buildings are naturally ventilated or mechanically assisted ventilation. And then he's made multiple regression models of all these factors against electricity use and fossil thermal use these are primary schools. So these results are a little perplexing in some cases, a bit difficult to comprehend, but can you read any of this? I'll read these out for you. Can I see them? This is floor area. So this is having a negative effect. This is the most important variable on electricity in primary schools. And it must be something to do with the fact that as the schools are getting larger, they've got more floor area that's being used for less, has less intensity of electricity, maybe circulation or fires or other kinds of things. Well, that's one possible explanation. This is pupil density. Again, one might expect that relationship. This is the glazing ratio. Here's volume to surface. So it's the fourth most important. This is external shading on the south. So this is something to do with maybe lighting. What is this one here? That's the glazing ratio, the negative effect, and this is, I can't really do this. This is age. So some effects, and volume to surface has some impact. Going to fossil thermal, compactness is the most important factor of all those considered. Then comes something which is very surprising, which is the obstruction facades on the north. Why would that happen? I mean, here is obstruction of facades on the south. One could understand that that might reduce solar gains, but this is a bit mysterious. This one is building age, again, quality of the fabric, and this one is whether the buildings are ventilated mechanically or naturally, which again, that's a rather unsurprising effect. These are the effects on secondary schools, less factors here, fewer factors rather. No geometrical variables with electricity. This is external shading on the south, something to do with lighting, presumably glazing type. Again, this is internal environment, which again, it's not surprising it affects electricity. Here in fossil thermal, this is pupil density. Again, one can imagine reasons perhaps to do with hot water heating, hot water supplies. And here is volume to surface having a negative effect because Sungmin has reversed the ratio. So that's of secondary importance in schools. Now, one should say that even these variables don't account for all energy use. The fractions are only 22% of electricity and just 9% of variation in fossil fuel use in primary schools. The figures are higher in secondary schools, so the models account for 34% of electricity, 41% of fossil fuel use, and other factors that might account for the remaining variability, well, one could speculate. They could be hours of use, boiler efficiencies, controls on lighting, the extent of IT equipment, probably very important in some cases in secondary schools. But so there's scope for further work, but once again, it's clear that geometry does play its part, especially in relation to energy use for space heating. Compactness, as we saw, is important for primary schools, and the ratio of surface to volume being quite important for secondary schools. My second non-domestic type is offices, going back to offices, for which there are several empirical sources of data on energy consumption in the UK, including display energy certificates for public office buildings, and one can, to some extent, compare buildings of different geometrical forms. I'm going to focus on big multi-story office blocks, but it's worth remembering that a large part of the existing office stock is actually in small buildings of domestic scale, and quite a lot of it indeed in converted houses. But large office buildings, I've made another case study in my book of high-rise offices in New York and Chicago from 1870 to about to the Second World War. And during all that period, these buildings were daylit, as I said before, and naturally ventilated. There was a bit of mechanical ventilation in the 20s and 30s, some electric lighting, but they depended basically on natural ventilation. And so for that reason, they were limited in depth, as I said. This is the Monadnock building, 1891, Chicago, on a long, thin block. And it's the width of the block determines the width of the building, which is actually in this case 18 meters. But it's just 2 rows of office rooms with a central corridor. Did I say tallest building ever constructed in load-bearing masonry? Tallest office building. But on other shapes of site, large square blocks that they have in Chicago, some of the office rooms could get their light from the streets, but others had to rely on light wells or courts at the rear. And as a result, these buildings tended to be L-shapes or U-shapes or complete courts, with again this dimension, 15 meters or so. You can see the scale. Okay. Now, Philip Oldfield and Dario Trabucco and Anthony Wood have made a very interesting historical study, perhaps some of you have seen it, of energy use in tall office buildings, concentrating on America, beginning with this period from 1870 to 1916. Because these were naturally ventilated buildings, levels of electric lighting were low or non-existent. The main uses of energy were almost certainly for space heating and lifts, although Oldfield and colleagues don't have any actual consumption data to show that. Glazing ratios were typically between 20 and 40%. This is the Liggett building, 1922 in New York. It's quite a deep building, but it has a core that's devoted to the elevators and the service core. And again, the offices themselves are all naturally ventilated. I've guessed that this is a glazing ratio of about 20% perhaps. Facade U values were high, single glazing, windows were leaky, but the use of masonry cladding created some thermal mass. In the central business districts of Chicago and New York, the numbers of high-rise buildings grew rapidly. In the Loop in Chicago, in the south half of Manhattan. And this growth gave rise to several problems. This is the Equitable Life Assurance building in New York, 1913, the biggest office building in the world when it was built, 38 stories. Still all naturally lit. It has these, as it were, 3-sided courts. But it was so big, rising sheer from the streets, that it overshadowed its neighbors. It cast a 7-acre shadow. It was said at the time that it reduced the value of adjacent property by more than $1 million. And there were other problems of congestion on the streets when people came out of the buildings, the load on the services and so on. And as a result of these, and also the creation of canyons with very dark conditions down at the base, down at street level. And this phenomenon of these very large buildings gave rise to a lot of public agitation, and in the end the passage of an ordinance in New York in 1916 which limited the bulk of buildings. And these are some diagrams by Harvey Wiley Corbett and Hugh Ferris, the illustrator, to show what the effects of the ordinance were. Basically, you were allowed to build up straight from the street line up to a limit of height which is determined in relation to the width of the roads. Then you had to set back the building at an angle and in practice you would set it back in a series of steps. And then you could have a tower whose height was unlimited, but it had to be not more than 25% of the area of the site. And so this created the kind of what became known as the setback style. And this diagram shows the Equitable Life Assurance building as it was actually built, 1913, before the Ordinance, and what it would have to have been after the Ordinance. So you can see how it could only rise to here, straight then be set back, and this is the 25% tower. So a very considerable reduction in floor space. And this is how the skyline of Manhattan came to be, because of the passage of the Ordinance. There's the Empire State Building at the back there, lots of these setback buildings. Now, Oldfield and colleagues have made some measurements of 10 buildings, 5 of them before the Ordinance, 5 of them afterwards. And on the y-axis is surface to volume. And you'll see that the average for these 5 buildings before is just above 1, and it rises, just above 0.1. It rises to 0.15 afterwards. These are actually probably larger buildings, but that would work in the other direction. So clearly the Ordinance has had a very significant effect on surface to volume, and one imagines, although Oldfield and colleagues don't have data, on the use of energy for heating in winter. How am I doing for time? Okay. It was Willis Carrier and the Carrier Engineering Company who introduced, with some others, who introduced air conditioning. Air conditioning in its first applications was not for the comfort of humans inside in buildings. It was for factories where the products and the processes were sensitive to moisture, like the production of chocolate or pasta or gunpowder, printing. The first building type where air conditioning was introduced to keep people comfortable was the movie theatre. In fact, the movie theatres introduced America to air conditioning. And people went in the summer, they were attracted by the low temperatures as much as the movies. This is the Rivoli, you see, cooled by refrigerating plants. These are enormous attractions. Then there was department stores, and in the late 30s, the Carrier Company built the first high-rise office building to be air-conditioned in full. This is the Milan building in San Antonio in Texas. It had air conditioning plant on one plant for for 2 floors, and the conditioned air was supplied through ducts in the ceilings of the corridors. Rather surprisingly, this is still a shallow plan building. This could still be naturally lit. But Carrier realized, of course, as did many of his contemporaries, that the introduction of air conditioning could allow much deeper plans. And I'll show you the consequences in a moment. The number of air-conditioned buildings grew very fast in America after World War II, and the substitution of fluorescent tubes for tungsten lamps reduced the internal heat gains. There were several other trends between the 1950s and 1970s, besides air conditioning, contributing to a huge increase in energy use per square metre in tall offices. As you all know, masonry-clad facades were replaced with glass. Glazing ratios went as high as 70%. Facade U values rose to values 3 higher. Huge heat losses in winter. Overheating from solar gains in summer. There was a fashion, I was going to say short-lived, it wasn't so short-lived, insane fashion for black glass skyscrapers. This graph shows dates from 1950 to the present day. Y-axis is numbers of black glass skyscrapers. The 2 dates here, 73 and 79, are emphasized because those older readers will recognize that this is the energy crisis in the 1970s, the rise of OPEC, huge increase in the price of oil, and suddenly people realize, whoa, well, maybe glass skyscrapers are not such a good idea. There was a great reaction from the 70s, of course, in office design, much research devoted to new kinds of glazing, new building codes, facade U values brought back down to 1.5, 1. Levels of artificial lighting which had been increased, despite these being glass buildings, were nevertheless brought back down again. But of course, many glass skyscrapers continue to be built worldwide. Some of us wonder why. Here's a study by Stein. Figures, these are 86 buildings in Manhattan, built between 1950 and 1970. These are averages for those buildings in each of these 5-year periods. This is the energy use. But this is primary energy use. Obviously, steam and electricity are not primary energy uses, but I imagine these are estimates of what is needed to provide the steam. This would be the consolidated Edison district heating of Manhattan. And you'll see that there's a doubling of average use just in those 20 years. Coming to today, here's some figures from the Better Buildings Partnership. These are contemporary buildings. Can you read this at all? So this is carbon dioxide emissions in this case.
Possible to ask somebody to drop the blind on this slide.
This is a very faint slide, I'm sorry. Can you see this? It's not a good slide in the first case. Is that better? Can you see a bit better? Anyway, this is a large number of buildings. Have we got any lights? Well, there are lights at the back there, yes, yes. Indeed, we could. We could turn the air conditioning on. Anyway, just to explain, this is numbers of buildings. Sorry, no, this is a big pardon. This is CO2 emissions. Each line here is a building, and they're divided into no air conditioning, standard air conditioning, and prestige air conditioning. Now, I'm not quite clear what confers prestige on some air conditioning, except that clearly it produces more CO2. And these are some figures for retail buildings, again from Better Buildings Partnership, divided into air-conditioned and non-air conditioned. And there's a third category, open. I don't know what that is, but it's certainly using a lot less energy. And of course, air conditioning is growing in retail, not just in big retail sheds, but also in small retail and in restaurants and so on. Okay. I'll come back to air-conditioned offices shortly, but how can one generalize these kinds of results? This has all been a bit anecdotal. But how can one say something more general about the effects of these geometrical variables across large numbers of buildings, large parts of the stock? Steve Evans and Ian Hamilton and I have tried to do that for the whole of London. And we've used a 3D model of London called Virtual London, which is produced by our Centre for Advanced Spatial Analysis. This is built from the footprints in digital maps, and the heights come from so-called LiDAR measurements, overflying aircrafts bouncing lasers off. So this model extends out to the M25 and can be used, and Steve Evans has made automatically measurements of some of the things that I've been talking about, surface areas, plan depth, for all these building blocks, of which there are, of course, a very large number. Now, the problem with this is that although we have detailed measurements for each of the blocks, there are not accessible energy data building by building. The Department of Energy publishes aggregate statistics for larger areas, for boroughs, and for 2 census districts, so-called middle layer super output areas, MLSOA, and lower level super output areas, LSOAs. And so we've had to look at those kinds of geographical units in order to make comparisons of the geometry with the energy use. And this is total exposed surface area by these quite small units, LSOA, and this is not surface volume, it's just surface area. And the black figures are the ones where there is more surface, and as one might perhaps expect, that's in the center, and perhaps going out, these are along the the Thames to the east with the big office development and so on. And we've looked at the statistical relationships between that surface area, just surface area, not surface to volume. We don't actually have floor areas. So this is surface area to gas on the left. So this is surface area. This is mean gas demand per meter by boroughs. And you can see there's a strong relationship. I can't remember what it is, but it's quite a high statistical relationship. Yes, for gas and electricity, the correlation coefficients are 0.82 and 0.76. There are no figures that we know of except display energy certificates on the extent of electric heating, but perhaps there's some effect of electric heating here as well as air conditioning. Notice in the electricity figures that certain boroughs stand out above the regression line. There's the City of London, Tower Hamlets, and Westminster, and those of you who know your London will recognise that those are boroughs with large concentrations of big office buildings. So there could be several effects going on here, but one might imagine this is at least partly to do with the presence of more air conditioning and perhaps more IT and so on in offices. This is volume to wall ratio, so this is half plan depth. Again across London, again by these small units, these LSOAs. And you can, well, it's unfortunate that in this particular slide a great range of plan depth have been grouped together in the blacks, which are in the centre and again out to the east, and some rather surprising places, Heathrow. These kinds of depths here, this is half depth, so this is the kind of thing you would expect for domestic or slightly larger scale buildings. The average half depth across the whole of London is, if I remember, is about 3.5. No, sorry, forget that. Getting lost here. But here are the same measurements as before. So this again is volume to wall ratio, half of plan depth. This time we've got a much greater range of values shown, and this is by 1 square kilometres in this case. So that the greens and the yellows are domestic kind of scale, the yellows getting up to 14, 15 metres deep. The really deep plans going up as much as 20, 30, 40, 50, even 60 metres deep are these reds and oranges. And when I first looked at these results, I thought, this is strange. I mean, in the city, this is plausible. This is Canary Wharf and down the Thames. Okay, that's plausible. This is Croydon, so that's some tall offices there. But what's all these deep buildings in Heathrow and up the Lee Valley? What are they doing? So, if you look at the maps, up there, Chingford, there's lots of warehouses and factories, which are very deep in plan. So that's okay. And in Heathrow, of course, there's lots of hangars and warehouses and some manufacturing. So those are deep plan buildings, very deep. But they could, a lot of them would be single story, a lot of them could be lit from the roof. They might not be artificially air conditioned. They might not be air conditioned, they could be. Elsewhere, of course, there would be some large retail sheds. So these are regressions of electricity and gas against plan depth. And in this case, we've actually doubled plan depth, but doubled half plan depth. So we've got depth. So this is actual depth measured in the way described, going up to 18, 20. Again, by boroughs. Slightly weaker correlations and with surface area, but significant nevertheless. And again, with electricity, you see these office boroughs rising above the regression line. And you see in the City of London, the average depth of all non-domestic buildings is over 20 meters. So here's a lot of office buildings that must be air conditioned. And here are picking out a small selection of boroughs, of which 3 are these. This is the City of London, this is Tower Hamlets, this is Westminster. This is mean plan depth, and you'll see that here is the City of London. And this is electricity intensity, now particularly high in the City of London. Of course, the problem with this is that one can't pick out in these relatively large areas just the deep office buildings, but I hope you'll be convinced that this is at least suggestive of a threshold in electricity use around this 15-16 meter kind of depth, above which electricity use rises sharply. And this is a further set of statistics which are to do with MSOAs in this case, again looking at plan depth, but picking out MSOAs in which there is a particular preponderance of non-domestic buildings of a particular type. And here there's more than 60% offices in these particular MSOAs, and you'll see that the regression is particularly steep against electricity use. I think, given the time, I'm going to jump a little bit here and just mention rather quickly how one might start to take this kind of research forward, but look at individual buildings, which would obviously be much more satisfactory. We were limited in this London study by the lack of data, of energy data at a building scale, and we were forced to look at aggregate effects. But my colleagues Rob Lydiard and Steve Evans and I have been working on a new study in which we're building 3-dimensional models of all buildings, in principle in the whole country, automatically. Sounds rather strange, but the way we're doing it is that we're taking footprints from digital maps and we're linking those by their addresses to data that comes from the Valuation Office Agency, which surveys the great majority of non-domestic buildings for the purposes of levying commercial rates. And they survey the buildings floor by floor, and they record their floor areas by floor levels, and they break down that floor space into sub-activities. So this kind of building, they would tell you that UCL is on whichever floors it is on, and that on those floors it has a certain amount of office area, and it has kitchen, and it has storage, and so on and so on. So this is very diagrammatically, you must imagine that here is a footprint in the digital map, and that with their addresses we've linked some premises, hereditaments. They're not buildings, they could be occupiers. In this building we have one building, but we have several occupiers, some of them commercial, some of them UCL, and we know which floor levels they're on. And again, we can get the overall heights from LiDAR. And once those models are made, we can take off, again automatically, the kinds of measures that I was describing, so that we can take volumes, exposed surface areas, so we can calculate that this is a party wall, but that this part of the wall is exposed, and so on. Could, in principle, calculate compactness. And so we're making a special study of the borough of Camden, because we can go out and look where we're unsure what's going on. So this is New Oxford Street. That's the British Museum, for which we don't have any floor area. And this is the dominant activity, color-coded, on the ground floor of, they're not buildings, we've defined a special unit which we call self-contained unit. The importance of the self-contained unit is that it has a clearly defined envelope for which we know the energy use, and we know where the heat is being lost or gained, and also that it doesn't cut any premises, so that if a shop has gone next door into what you might think of as another building, we would include the two buildings together in one self-contained unit. So these are self-contained units. And here the yellow, unsurprisingly, is retail. The reddish is office. And then if you look at the predominant activity on all floors in the same area, this is predominantly office, although some is retail on several floors. And here's a view of part of the 3D model. This is Mornington Crescent Tube Station. This is, for those of you who know it, the old Carreras cigarette factory, Camden High Street. The grey is domestic, but it's important to know where the domestic is, because in many cases in a place like Camden you have flats above and shops or restaurants, cafes down below. That's the blue building is the Coco music venue for music enthusiasts. This is one of the buildings in that view. This is the Crowndale Centre, which is a Camden office building. And this is just to illustrate that we do know from the valuation office data what sub-activities are on which floor levels. This is a mixed building, has several kinds of uses, predominantly office, which is this pale colour here, but it also has storage and kitchens and post room and all kinds of other things on these lower floors. And in the last 6 months, that's the end of the slides, in the last 6 months we have had access from Department of Energy to individual gas and electricity meter data for every premise in Camden, including domestic. You mustn't tell the Daily Mail. We have it under very strict conditions of confidentiality, but the point is that we can now begin to look at some of these effects statistically for large populations of buildings, building by building. Rob Lydiard, who's here, has been looking at energy intensities by activity, which is obviously the first kind of thing that one might do with these data, and compare with other historical sources and other databases. But in relation to the topic of my talk, clearly what this this work offers the prospect of is looking at geometrical effects for very large numbers of buildings statistically in the way that I've tried to describe. And in principle, since these 3D models are created automatically, given enough computing power, we should in principle be able to extend it to the whole of the country. Whether we can get the whole of the everybody's gas and electricity bills for the country is another matter. So, thank you very much.
Well, that's what 30 years of research looks like. I guess approximately. Phil,
yes.
Would you be prepared to take any questions?
Yes, of course, if people can stand it, yes.
So, while you're thinking of your questions, Phil, can I just
yes, please.
You said, I think at one point, that the geometrical relationships themselves are mediated by technologies such as lighting and heating technologies,
Yeah, sure.
insulation technologies, and so on.
Yeah.
Have you, or has anybody else to your knowledge, looked at the possibility that geometrical relationships themselves vary over time for individual buildings, rather than for collections of buildings which change as new buildings are built?
Geometrical varies over time for the same buildings.
For the same buildings, yes.
Am I understanding you right, Bob? Are you imagining buildings?
The effects of geometry on
yes.
consumption.
Yes. As they change their technologies.
As the internal technologies change.
Yes.
Has anybody detected that?
Well, I mean, the problem with all this kind of work, and the reason I was, in a way, sort of scratching around for material in the talk, is that people haven't done these kind of large-scale, as we would call them, epidemiological studies, mainly because of lack of data, and for historical studies, that lack of data is even worse. I mean, Oldfield and colleagues tried to do something over this long time scale since 1870, but they were really speculating. I mean, I started reading their paper thinking, this is great, we'll learn about what's energy use over this whole long period. But of course, they don't have it. They only have suggestive bits of data here and there. So I don't know anything, no, but it would be fascinating if one could find anything of that kind. One can, I mean, I suppose there is a kind of proxy for age in the sense that one can look at buildings of different age that exist today and maybe find something of that. And interestingly, you can find some rather efficient old buildings,
Yes.
not just that they're naturally ventilated, but for other reasons. Yeah. Please.
In Southampton and Woking,
Yes.
they've got district heating systems where they're taking energy from buildings which are dumping energy into buildings where they're using energy.
Yeah.
With this sort of modelling, would you be able to do that?
Well, we're looking in the first place just at gas and electricity use annually in each building. In the work that I was just mentioning, Camden work. The advantage of a geographical approach is, of course, that one could begin to look at that kind of grouping of buildings spatially and potential for that sort of thing. I mean, technically, from our work, Rob will agree if this is or not, technically, district heating is problematic for us because we need to know which bits of floor area are served by which systems and by which meters, and that's really tricky. You can know that a meter is in a building or in a group of buildings, but who is actually, at the end of the wire or the pipe is not so easy, particularly in buildings that are mixed, domestic and non-domestic, or that have mixtures of non-domestic uses. But in principle, it would be nice to look at those kinds of things. I'm also interested myself, as you can imagine, in looking at issues of density in relation to this kind of modelling. Well, that answers your questions.
Did you have a question?
Carl.
This is interested in obviously taking the historical perspective.
Yeah.
The change in standards.
Yeah.
In terms of VRE, in kind of excavating some information that it had on some early work on, like back in the 40s.
Yeah.
They found the records of the kind of reference temperature for the work they did was 15 degrees Celsius. And so, in terms of what was acceptable
Yes.
as
Those
a
things change.
standard level for
Yes.
heating,
Yes.
comfort,
Yes. Yes.
change fairly significantly.
It goes up and down, yes, quite, yes. I mean, it's interesting that the rise in, the raising of levels of lighting and so on in office buildings before the 70s crisis, and then reductions afterwards, and then the kinds of things that Bob knows a great deal about, the recent history of the building regs. So yes, of course, they change and would change demand historically. But what you're saying, that would be jolly interesting, or what is your question?
Factor you need to take into account in terms of rising
Yes, sure. Well, to be honest, given the state of knowledge of the non-domestic stock in Britain, of course there's a great deal of knowledge of particular sectors of it, but as a whole, we're in the dark in large parts, and it's our first ambitions with this work I was just describing to kind of get a grip on the present situation, see what is being used in what kinds of buildings. We've taken Camden because it's, we can go out and look at it. But it's mainly offices and shops. The real terra incognita is industrial buildings, which are the biggest sector. People think that Britain is a post-industrial country. It's not. Certainly there's an awful lot of buildings out there. But the extent of knowledge is very, very weak. And so if we can find out more about that, building by building, with actual energy consumption, then I think we could go a long way. But what we don't have is comprehensive, or even, part comprehensive data on internal temperatures, or even the extent of air conditioning, or a lot of things we would like to know. The kind of things that St. Min and Co were collecting laboriously for schools. It would be very nice to know more about those kind of things in a larger selection of building types.
Time is running on, and I guess somebody would probably like to join us upstairs. I'll take 2 more questions, and then I think we'll wrap up. So can I take the chappie at the back?
I just had a quick question about the energy data that you're using, the LSOA scale.
Yes.
So as far as I'm aware, the data includes basically all meter readings above a certain floor size or thereabouts. That would include commercial, building-related energy as well as industrial process energy. And I was just wondering whether you'd adjusted for that in your regression.
This is all electricity and gas meter data. So for the industrial uses, there would be process in there, but it's not. It's meters of any kind of. It's all meters. It's not. There's no threshold other than the fact that DEC, who publish the statistics, this is perhaps what you're thinking of, have an arbitrary figure by which they distinguish for gas between domestic and non-domestic. They also, for various reasons, don't publish the electricity data or parts of it at the lowest scale of aggregation, because I guess then individual users might be identified. And so we were missing, in the London's work that I showed you, we were missing some users because they were electricity, because it was aggregated to boroughs, and therefore it was not useful for that kind of work. But for the Camden work describing, we have all meters. Yes, domestic, non-domestic, industrial, everything. Some of it we're wondering, we have a perpetual conversation, Rob and I, as to where the underground gets its electricity. And we still haven't found out yet. I think it might be in Westminster. Westminster consumes a staggering amount of electricity. But who knows?
One more question? Yes.
I was wondering about lightweight buildings, if you have surveyed them, and if in that case the relationship between form and energy consumption is still similar to the ones you have found for traditional buildings.
Well, we're in principle looking at all kinds of buildings. Of course, one would expect the consumption to be significantly different. The only data that we have in the London work, it was just geometry, and we had no data on construction or fabric or of any kind. In the Camden case, there is a firm that we've commissioned to make surveys of materials and structural systems and to make estimates of age of all buildings, which they've just delivered to us. But those are external surveys, so what they will tell us quite about, fabric U values and so on, it's guesswork. But we'll have some indication. We'll know that these are masonry buildings or these are curtain wall or whatever. But that's as far as we get. The valuation office itself, who publish the floor area data, do collect data on fabric and materials and age, but they don't make them available. Yet, they might if we persuaded them.
Okay, Judith, this is a quick one.
Very quick, slightly conjecture as well.
A quick question from Judith.
Because we are not talking a lot about data and where it comes from.
Yeah.
Just how would you estimate the amount of time you spend and the team spend acquiring data versus analysing it?
Well, acquiring is a matter of paying over sums of money and some political negotiation, which can take a great deal of time. I think the important thing is that the getting data into usable order, that's the really time-consuming. I mean, particularly the valuation office data, which again Rob could talk about. It's not designed for the kind of work that we do. It's not collected for statistical purposes. It's for rating. And they're quite casual in some of the kinds of things that we would think were very critical. They're quite good at classifying activities, but in other respects they do all kinds of naughty things, which takes a great deal of work to sort out. And what is also very challenging, I didn't say very much about it, I passed over it, very challenging in the kind of work we're doing in Camden, is to match addresses. I mean, it's easy to say match addresses. In fact, that is a real black art. And enormous amounts of efforts have to go into that, because the formats of addresses could vary. People are not consistent. You can have Sainsbury, J Sainsbury PLC, Sainsbury Supermarket, all of which we can recognise as the same thing. But computers, it's another matter. So there's a huge effort there. And then there's the question of what is addressed. Is it the first floor of Central House? Is it Central House? Is it 14 Upper Woburn Place? There's a whole huge business there. So those are the time-consuming things.
Happily, we have experts in black art.
Rob, yes, I'll take that. Rob is one of the black magicians.
I would like to thank Phil for an absolutely fascinating talk, for so generously answering questions. So if you'd like to join me.